In this class, let us learn diffraction of light. Have you noticed how you can hear someone round a corner before you can see them? This is due to diffraction of sound waves. The bending of light around the corners of small obstacles or apertures and its consequent spreading into the regions of geometrical shadow is called diffraction of light. The diffraction effect is observed if the size of the aperture or the obstacle is of the order of wavelength of the waves. Here you can see the diffraction effect in the case of a wide aperture, wide gap. Diffraction effect is small. But in the case of a narrow gap, narrow aperture, you can observe large diffraction effect. Light has a very small wavelength, so only very small objects or gaps can affect its direction. The wall blocks the light and the person can't see around the corner. But sound waves bend around objects of similar size to their wavelength. The wavelength of sound is large, so sound gets easily diffracted. As the wavelength of light is much smaller than the size of the obstacles around us, diffraction of light is not easily seen. But sound waves have larger wavelength, so they get easily diffracted by the objects around us. Let us learn diffraction at a single slit. When a single slit is illuminated by a monochromatic source, a pattern with central bright region followed by alternate dark and bright regions of intensity is seen on both sides of the central bright fringe. Here is a slit. The wave gets diffracted. As a result, a diffraction pattern is observed on the screen. The central fringe is known as central maximum, having maximum intensity, and the width is also maximum. And the intensity goes on decreasing on either side of the central fringe. This pattern is known as diffraction pattern. Let us consider a parallel beam of light falling normally on a single slit AB. A single slit AB of width d, small d. A plane wave is incident on the slit AB. Capital D is the distance of the screen from the plane of the slits. O is the center of the screen. Each point on the incident plane wavefront acts as a source of secondary waves according to Huygens principle. And the waves traveling in the direction of the incident beam converge at O. There is no path difference of the waves on reaching O, and the waves constructively interfere to give maximum intensity, and that is the central maximum. Let us consider the waves diffracted at an angle theta. The waves converge at P, which is at a distance y from O. Capital D is very, very large compared to width of the slit small d and the distance of the point P, y. Let us find the path difference between the edges of the slit A and B. to reach the point P. Let the path difference be x. In order to find the path difference, let us draw a normal AN on BP. The path AP is equal to NP. There is no optical path difference between AP and NP. So the path difference between AP and BP is BN. So BN is the path difference between the edges A and B of the slit. Let it be x. X is equal to BN. The angular position of the point P is theta. So the angle BAN is also theta. So let us consider the right angled triangle ANB. Sin theta is equal to opposite side BN by hypotenuse AB. BN is the path difference x by AB is the width of the slit D. Now let us consider the triangle COP. It is a right angled triangle. Tan theta is equal to opposite side OP by adjacent side OC. OP is Y and CO is equal to D. So tan theta is equal to Y by D. If the angle theta is small, sin theta is equal to tan theta, approximately equal to theta. So theta is equal to x by d, that is equal to y by d. So the path difference x is equal to y small d by capital D. Or in terms of theta, x is equal to d theta. And now let us apply the condition for constructive and destructive interference. Let us consider the center of the screen. At the center on the screen, theta is equal to 0. All the waves originating from the plane wavefront AB travel equal distances and reach the point O in phase. They constructively interfere to give maximum intensity at O, and that is the central maximum. Now let us see the position of minimum. Suppose the path difference x is equal to n lambda, where n equals 1, 2, 3, etc. If n equals 1, x is equal to lambda. Then the slit can be imagined to be divided into two equal parts. AB is the slit and C is the midpoint. So slit can be divided into two equal parts, AC and BC. Path difference between A and B is lambda. So the path difference between A and C is lambda by 2. So the points A and C are out of phase. So we can say the waves from the region AC will be out of phase with the waves from the region BC. Since the waves are out of phase, they cancel each other or they destructively interfere with each other, and the resultant intensity at the point will be 0, or that is the position of first minimum. For the first minimum, path difference x is equal to lambda. But x is equal to y d by capital D. So the distance of the point y is equal to x capital D by small d. So the distance of first minimum y1 is equal to d lambda by small d, because for the first minimum x equals lambda. But x equals theta d. So the angular position theta is equal to x by d. Let us substitute for x equals lambda. So the angular position of first minimum theta 1 is equal to lambda by small d. It is independent of capital D. Similarly, for the second minimum, y2 is equal to 2 d lambda by small d. And so the position of nth minimum, yn, is equal to n d lambda by small d. And the angular position of nth minimum is theta n is equal to n lambda by small d. Now let us see the condition of maximum. Let the path difference x is 2n plus 1 lambda by 2, where n equals 1, 2, 3, etc. If n equals 1, x is equal to 3 lambda by 2. 3 into lambda by 2. Then the slit can be imagined to be divided into 3 equal parts: AC, CD and DB, 3 equal parts. The path difference between A and B is 3 lambda by 2. So the path difference between A and C is lambda by 2. And the path difference between C and D will be lambda by 2. And that between D and B will be lambda by 2. So the waves from the first 1/3 region AC is an out of phase with the waves from the second 1/3 region, that is CD. So the waves from the first 2 regions cancel each other. But the waves from the third part of the slit, that is BD, will contribute to some intensity at P, and that gives rise to secondary maximum. But the intensity of the secondary maximum will be less than the central maximum, because the waves from 1/3 region of the slit will contribute to the intensity. Therefore, for the first secondary maximum, the path difference is 3 lambda by 2. But x is equal to yd by capital D. So the distance of the secondary maximum, y is equal to xd by small d. For the first maximum, y1 dash is equal to 3 d lambda by 2d. But x is equal to theta into d, or theta is equal to x by d. So the angular position of the first secondary maximum, theta 1 dash, is equal to 3 lambda by 2d. Similarly, for the second secondary maximum, the distance of the point y2 dash is equal to 5 by 2 d lambda by small d. So the position of nth secondary maximum is given by yn dash is equal to 2n plus 1 d lambda by 2d. And the angular position of the nth secondary maximum is theta n dash is equal to 2n plus 1 lambda by 2d. The angular position is independent of capital D. Now let us find the fringe width of the secondary fringes. Width of the secondary maximum will be the distance between two consecutive minima. Beta is equal to y2 minus y1. y2 is the position of the second minimum, and y1 is the position of first minimum. So beta is equal to 2 d lambda by small d minus d lambda by small d, that is equal to d lambda by small d. And width of minimum is the distance between two consecutive secondary maxima. Beta dash is equal to y2 dash minus y1 dash. It is equal to 5 by 2 d lambda by small d minus 3 by 2 d lambda by small d. That is equal to d lambda by small d. The secondary maxima and minima are of equal width, and the angular width is lambda by small d. Let us see the width of central maximum. Width of central maximum is the distance between first minima on either side of the central maximum. So width beta 0 is twice y1, 2y1. That is equal to 2 d lambda by small d. And the angular width will be 2 lambda by small d. Width of central maximum is twice as that of the secondary maxima and minima. This is the intensity pattern of diffraction. The first minimum is at an angular position lambda by small d. Second minimum at 2 lambda by small d. The intensity goes on decreasing as we move from the central maximum. But the width of the central maximum is twice that of secondary fringes. Now let us see the differences between interference and diffraction. Interference is the double slit experiment and diffraction is the single slit experiment. So interference is the result of superposition of two waves from two coherent sources. But in diffraction, it is a result of superposition of a large number of secondary waves from different parts of the same slit. In interference, all bright and dark fringes are of equal width. But in diffraction, width of central maximum is twice as that of secondary maxima and minima. In interference, all the bright fringes are of same intensity. But in diffraction, intensity of bright fringes decreases as one moves from central maximum. In interference, the angular position of the first maximum is lambda by d, but in diffraction, it is the angular position of first minimum. In interference, there is a good contrast between bright and dark fringes because all the bright fringes are of same intensity. But in diffraction, poor contrast between bright and dark fringes. The double slit pattern on the screen is actually the superposition of single slit diffraction from each slit. So the pattern will be like this. Double slit pattern is actually within the central maximum of the diffraction. The actual pattern shows a broader diffraction peak in which there are several fringes of double slit. The number of interference fringes depends on the ratio d by a, where d is the distance between the slits and a is the slit width. When a is very small, tends to 0, the diffraction pattern becomes very flat and we will observe only interference. So if there are finite number of sources, for example 2 or 3 sources, we use the term interference. But if there are a large number of sources, we use the term diffraction. Principle of conservation of energy. In interference and diffraction, light energy is redistributed. If it reduces in one region, producing a dark fringe, it increases in another region, producing a bright fringe. There is no gain or loss of energy, and which is inconsistent with the principle of conservation of energy. Thank you.